back. Okay, so I mentioned looking back in time there. So that's key. So is that possible? That's the time machine aspect of this talk. So we're looking back in time, question mark. Is that true? The answer is yes, because you're always looking back in time. Okay? If someone's standing 1 meter away from you and you're having a conversation, that image that you see of them is actually from the past. It's the near past, because it only takes 3 nanoseconds for that image to get from the person you're talking to your eyeball. And this is pretty short. It's a very, very, very small fraction of a second. And so we typically refer to that as instantaneous. We can't really perceive that short amount of time. And so everything seems like it's happening instantaneously. But what about objects that are further away? The sun, for example, is 8 light minutes away, which means the light from the sun takes 8 minutes to travel to us. So if the sun exploded, we wouldn't know about it for 8 minutes. As you go further away, the nearest star is about 4 light years away, which means the light from that star takes 4 years to get to us. Okay, so if we take a picture of that star, we're not seeing that star today, we're seeing that star 4 years ago. Okay? And as you make the distance larger and larger and larger between you and the light emitting object, you're seeing that object at some time in the past. Okay? The other side of our galaxy is about 100,000 light years away, so that light takes, just even inside our own galaxy, takes about 100,000 years to get to us. The nearest spiral galaxy is about 2.2 million light years away, so we're seeing that way in the past. And the horizon of the universe, the cosmic microwave background, is 13.8 billion light years away. So we're seeing the universe 13.8 billion years ago if we look at the cosmic microwave background. And that's what I study. So the advantage to that is you're seeing essentially a picture of the infant universe, and you can study that. You can see what did the universe look like when it began, and then you're able to also look at the universe around you, and you can start to understand how the universe evolved. Okay, so we talked about expansion, so let's talk about the early universe now. What if we reverse time in our minds, and instead of everything moving away from everything else, everything is moving towards everything else, right? Then at some point in the past, everything was going to be on top of everything else, and the universe would therefore be a hot and dense plasma. So what is a plasma, first of all? We're very familiar with plasmas. The sun is a plasma. So a plasma is something that's so hot that the charges can't combine together to form, for example, hydrogen. You have free protons and free electrons bouncing around with some photons, and so therefore you have charge. There's charged particles, and you have photons, and everything's very hot. That's the takeaway. And that describes very well the surface of the sun. There are other examples, lightning, for example. This would be plasma, right? So you have a large voltage that's able to tear electrons away from the atoms in the atmosphere, and therefore you have charge, and you have current, and you have photons. You have a plasma as well. So this is what the entire universe looked like at the very beginning. It was just a plasma. Okay, so this plot is trying to explain that. This is the ionization fraction plotted versus temperature. And so the temperature of the universe now is way over here somewhere, but if we're going backward in time, right, the temperature is getting hotter and hotter and hotter and hotter and hotter and hotter, and we get to 3,000 Kelvin, it gets hot enough that we start to form a plasma. And so the ionization fraction goes up, and then eventually, by the time you get to about 4,500 Kelvin, the universe is completely ionized. And therefore you have a plasma. And so if we keep going back in time, the universe over here is going to be a plasma. We can't see through a plasma. It's like looking into the sun. It's opaque. In this part of the region, in this region of the plot, or in this universe here, the universe is transparent, so you can see things. In this region, the universe is opaque, and you can't really see very far in front of your face if you could survive in the 4,500 Kelvin environment. So just for calibration, this is approximately 5,000 Kelvin is approximately the temperature of the sun. So it's very hot. If we plot the brightness as a function of frequency for a 3,000 Kelvin body. It looks like this, which doesn't mean much to you, but it has a very nice theoretical shape. It's called a blackbody. And what I've noted here at the blue bar is these are the frequencies that the human eye can detect. You can see these frequencies of light. These appear to you as colors. So a different frequency looks like a different color. So as you go across this box here, you're seeing different colors. Okay, so you can very nicely see with your eye a 3,000 Kelvin body, right? But what's happening is this is the early universe, right? It's very hot, and therefore this is what you have. Now if we reverse time again, so time is going in the forward direction, our 3,000 Kelvin body is going to cool. It's going to turn from a plasma into neutral hydrogen and photons, and the universe will become transparent. And as it continues to expand, the remaining photons will cool as the universe expands. And so this very hot spectrum over time turns into this spectrum, which is a 3 Kelvin spectrum, close to absolute zero. So for calibration, absolute zero is minus 459 Fahrenheit. So this is about minus 450 degrees Fahrenheit, a body. That is, that temperature will emit light in this way. Okay? So the important thing to note here is we may have a solution in part for Olber's paradox, because here's an optical image of the entire sky, and this is probably what you're accustomed to seeing, a lot of black, right, with dots, right? This is coming from the fact that your eye can see here, but the universe now is filled with photons, with light, at these frequencies, and so you don't see anything. It's black. But does that mean there's nothing there? No. There's a lot there. You just can't see it. Okay? So this background radiation was serendipitously discovered by Penzias and Wilson. They wrote this paper in 1965.